Yeah, hi everyone, so my name is Michael, and that's the first paper for the assignments. The title of the paper is called Applying Deep Learning to Reduce Large Adaptation Space of Self-Adapted Systems with Multiple Types of Goals, and it's written in 2020s. And what's the problem the paper tries to solve? So when self-adapt systems needs to adapt, it has to analyze the possible options for adaptations called adaptation space. The analyze process can be a resource and time consuming. The paper is then try to solve the problems with one approach, that is using deep learning techniques to reduce the adaptation space to only the relevant adaptation options. And why is it still a problem? Because there is no solutions at the moment that can effectively ensure that the reduced adaptation space is significantly smaller. High performances means that the reduced adaptation space covers the relevant adaptations options well. The other reason is that the effect of the space reductions on the realizations of the adaptation goal is negligible, and also there is no notable effect on the above 3 points for a larger size of the adaptation space. The earlier works that applies machine learning techniques to reduce large adaptation space focus on threshold goals only, and this paper is focused on both threshold and optimization goals. So the author's ideas propose two-stage learning approach called deep learning for adaptation space reductions. They try to investigate whether deep learning effectively reduces large adaptation space for both threshold and optimization goals without compromising the system's goal. In the first stage, a classification's deep neural networks is applied to reduce the adaptation space for the threshold goal. In the second stage, a regression's deep neural network is applied to rank the options, further reducing the adaptation space for the optimization goal. And what is the difference between the solutions? The existing solutions that are used to reduce adaptation space, including classifications, regressions, decision trees, and online learnings, only handle threshold goals only, while practical systems often need to address also more optimization goals. And the results shows that for setting both threshold goals and optimization goals shows the solutions is effectively with a negligible effect on the realizations of the adaptation goals. So for the evaluations, the authors evaluate the approach using identified two metrics to actually evaluate the performances of the trained learning model, and the third metrics to compare the effectiveness of the approach with others. So the metrics consist of precisions, which captures how many of the predicted adaptation options are relevant, and a recorded value indicates how many of the relevant adaptations options are predicted, and also if they combine it together into a single score called F1 score to actually evaluate the solutions and compare the solutions for the reductions of the adaptation space that is based on the threshold goals. And the experiment correlations is used for evaluating the rankings of the adaptations options based on an optimization goals. It conveys the values of the estimate quality properties for each adaptation options to numbered ranks. The authors defined an integrate matrix to compare the efficiencies of the different adaptations space reductions approach. It captures the average adaptation space reductions. And they also use simulators as experimentals with the real physical setup is time consuming and expensive. And the valuation with its results actually effectively reduce the adaptation space with a legible effect on the realizations of the adaptation goals. If we only consider threshold goals, this approach improves also over a state-of-the-art approach that is use classifications. And this new approach still need to be tested in a real world situations to see if there are any changes I need to make due to the simulations valuations.